So this video is about a short introduction to extended finite element method. So this method is proposed by Beltisco and his co-workers, especially for crack propagation, mainly for crack propagation studies. So as I said earlier, in case of finite element method, closer to the crack tip, if you have to go for reducing the elements remeshing, I end up remeshing the entire domain. So as the crack grows, I have to keep on remeshing the entire domain, which is time consuming. So if there is a method which do not require this remeshing, this mesh dependency for better results, that is more advantageous than the finite element method. Even if the crack propagates, if I do not require to change my mesh, it is much better. So XFEM offers this advantage. Okay, how XFEM offers this advantage? XFEM offers this advantage by using enriched elements. But in case of finite element method, even if I go for finer elements closer to the crack tip, because of the complex stress field closer to the crack tip, it is difficult to capture that stress distribution by using the lower order shape functions what we have in case of finite elements. So as to overcome this problem, in case of finite element method, we go for singular quarter point singular elements, where we move the mid-side node towards the end node, which helps in capturing the infinite stress in the crack tip. Okay. Usually when we perform finite element method by using this quarter point singular elements, we will be able to capture the stress field closer to the crack tip, and that stress field will be of, if it is we can write generally in this manner: r power minus 1 by 2 k1 f1 fij theta plus k2 f2 ij theta plus k3 fij theta plus higher order terms. So the stress field closer to the crack tip can be generally written in this form in terms of the first, second and third mode fractures, sliding, tearing and my open mode fractures, and these are mixed mode fractures. Okay. So if I have, once I get an expression for my stress field closer to the crack tip, to be precise, in case of mode 1 open type fracture, if I have sigma xx is equal to 1 by root of 2 pi r k cos mod k1 by root 2 pi r cos theta by 2 1 minus sin theta by 2 sin theta by 2. For sigma hx, sigma y I will be having 1 plus sin theta by 2 sin theta by 2. So if I get to know the stress field and the r is the distance from the crack tip, so once I get to know the stress field, I will be able to find my stress intensity factor. In case of brittle fractures we will not have any process zone around the crack tip, we won't have any elastoplastic zone, so we will be able to find the stress intensity factor. So once I get to know the stress intensity factor, if the stress intensity factor is less than the critical stress intensity factor for the material, then there will not be any progressive crack extension failure. Okay. So if I get to know the stress field closer to the crack tip, I will be able to determine the stress intensity factor and compare that with my critical stress intensity factor to know whether there is unstable crack propagation or not. Okay. So in finite element method, we use quarter point elements so as to determine the stress intensity factor, and thereby get to know about the crack propagation. But as I said earlier, even if I use quarter point singular elements, I have to keep on remeshing my entire domain as the crack grows. I don't want to do that, so I go for XFEM, because in XFEM we make use of enriched elements. In XFEM we go for enriched elements. Okay. So in case of enriched elements, besides the standard finite element shape functions, we have enriched shape functions, not for all the nodes which lie in the domain, only for those nodes whose elements are cut by the crack. Okay. So the approximate function will be given by sigma I is equal to sigma of all those nodes which belong to the total set of nodes ni ui plus summation of all those nodes which lie in the set of enriched nodes, which is the subset of total number of nodes mi psi. Okay, so this is the enrichment, and these are standard finite element shape functions. So I need to know what are all the elements in the domain which are cut by this crack. I'll get to know the information about the elements which are cut by the crack by using the level set functions in case of XFE. So level set functions. So these level set functions will have value of 0 in the crack interface, where they will have positive and negative values on either side of the crack interface. So if I want to determine whether my element is cut by this crack face, I have to find the least level set value of those nodes in my element and the maximum level set value of the nodes in my element. If the product is less than 0, then obviously my element is cut by the crack face. Okay, those elements which are cut by this crack are said as cut elements, are also called as reproducing elements, and these elements will have all their nodes as enriched nodes. So which are all the elements which are cut by this crack will have enriched nodes, and those elements which are adjacent to these reproducing elements which have part of their nodes as enriched nodes, while the other nodes as ordinary nodes are said as blending elements. And those elements which are beyond those blending elements will behave like normal finite elements. So the enriched function is usually taken as the signed level set function. The enriched function will be taken just as the signed level set function. So I will be introducing this enrichment only for those enriched nodes whose elements are cut by my crack face. Okay, so this method looks very impressive because I need not go for any remeshing. My mesh almost remains independent of the crack propagation. I have to just as the crack grows into different elements, I have to just add my enrichment function to those nodes whose elements are cut by this crack. So this element, X finite element method looks very impressive in case of crack propagation studies as against finite element method, where we have to keep on remeshing our entire domain as the crack goes. So how far this method is better when compared to mesh filling method, which was also proposed with the same function in mind. But the thing with the mesh filling method is, in case of mesh filling method, we are developing our interpolation function just by, it is more like a particle method, while in this case of XFEM method, it has its basis with FEM, so it is a continuum based method. So when we have problems like complete fragmentation of my structure of my domain, in that cases it is better to have a particle method rather than a continuum based method like finite element method or extended finite element method. So in those class of problems, the continuity aspect of mesh also comes handy there. So fragmentation sort of problems, mesh seems more attractive in those class of problems rather than XFEM method. Thank you.